OI, a comprehensive review of recommender systems transitioning from theory to practice. This is just an intro video, very, very high level. If you want to actually get into it with these systems, you're going to have to probably read not just this document, but all of the many sources, or some of, sorry, the many sources it lists. It gives a lot of good guides, foundational papers in the field, that kind of thing. So if you just want a high level overview of how these systems work, stick around. Personally, I'm interested in this because it's just good to see other subfields and what they're up to. I'm more of an LLM kind of person, but I figured this would be interesting today. And yeah, so like, subscribe, comment, all the YouTube things, join the Discord to discuss, follow on Twitter and LinkedIn. Join down below, hit that join button as low as $1 per month to support me if you're a big fan. And our traditional disclaimer, put me at either a 1 or a 3 today, depending on your point of view on things. But yeah, let's get started. So the math today is going to be on the simpler side. We're not going to get like seriously into how these models are working or actual architectures, right? We're going to list off and describe architectures, and if you have a deep learning background, then you'll be good on that, just hearing which ones they use, and you'll be like set. More so, what we're doing when I say simple math, I mean like high level, right? Very high level stuff. So not 1 plus 1, more like abstract, right? But very not super into it, and we should be able to just discuss it and not actually do any math seriously. But anyways, let's get into it. So one of these recommender systems can be represented as a function that predicts the utility of an item I for a user U, right? That utility denoted as r hat underscore UI. And the idea being it estimates how much a user would prefer that item. We then rank said items and provide said items to the user in order of ranking, right? Or some kind of order. Here we see the function with an input being a user, the actual item, and the function's parameters itself. Now, interesting with a recommender system as opposed to some other types of deep learning, for example, my background is more so in language modeling, is that you have this kind of continuous feedback loop where you don't, where in a language model, you would collect your data, you would do your training, and then you would start performing inference and you would never touch data or training again, kind of thing, right? Whereas here in a recommender algorithm, you actually constantly have to update your actual model, right? So you are not just starting off collecting data, you are actually, even after performing inference and getting your actual real world results, using that as further data to continue getting more data and to keep your training pipeline continuously going. I mean, I'm sure the scenarios you can pause it and just have a solid one, but generally speaking, most scenarios we have recommender algorithms, social media, shopping, e-commerce, stuff like that, is they constantly have new users entering the platform and new items hopping on too. So it's a more complicated problem in that sense than a lot of statically learned models. Now, the first type of RS is a content-based filtering, the strategy that suggests items to a user based on the attributes of the items and a profile of the user's preferences, typically utilizing similarity measures to match the user preferences with item attributes. Very simple one you see here, right? You have the user as input to some model theta. That model then outputs a vector for the given user, transpose that and dot product it with the vector that represents the actual feature of the item, right? So very simple here, dot product out gives you a scalar, similar ranking as we described before. Now, doing things this way does have some challenges. We will, throughout this video, be discussing all the challenges with every method we mention. And specifically with this one, content-based filtering faces challenges such as the cold start problem, meaning when you just have no data and an empty, randomly initialized model, you have to start from somewhere, and that initial start is a very tough point. Usually you want a collection of data, a lot of it, to feed into the model, but sometimes for a given website you make or whatever it is that needs a recommendation system, you might have to start with literally one data points, in which case your algorithm is really not going to be very useful, right? So a lot of websites will start off, websites, platforms, whatever, will start off with a heuristics based algorithm, as in not actual machine learning anything. They'll just show like most recent, for example, or based off keywords or like a website owner's pick or something. and collect data for a bit before finally having enough data to avoid the cold start problem. The next problem being overspecialization. This is when the model tends to only suggest items similar to those the user has already seen or liked. Huge issue. I don't know if you've noticed, if you use both YouTube and TikTok, YouTube, relatively to TikTok anyways, has a bit of this issue. When you watch something on YouTube, it really thinks you're going to love that genre forever and keep showing you that stuff. Whereas TikTok is a place that's very good at actually showing you new topics you didn't even know you would have liked, right? I might get into some point why the reasoning behind why that's happening, but let's get past that for now. And big one, computational cost. So in order to compare every single item vector to every single user vector, that wouldn't necessarily mean that as your number of items grow and as your number of users grow, so too does the cost computationally, which will increase quadratically. It says or cubically. I don't know what scenario leads to cubically, but whatever. It'll increase quadratically with the number of users and items. And the final issue with this method being, and this is really like issues common to all methods, but like especially strong with this method, there's a lack of updates to user and item profiles. Some user disappears for 6 months off Amazon, then comes back again. The odds that the previous recommendation algorithm and the vector that's already stored for that user is still good is not that great. Next method is collaborative filtering, which is a technique used to predict the preferences of a user based on the preferences of similar other users. This is further divided into two main categories, memory-based and model-based methods. So if we look at collaborative filtering, it splits into memory-based and model-based, right? And then memory-based further splits into user-based and item-based. Memory-based CF makes recommendations using similarities between users or items directly from user ratings. And a subtype of it is user-based. User-based CF predicts a user ratings based on similar users' historical ratings, while item-based CF predicts ratings based on similar items. This is really just a focus thing. In reality, for most of these models, depending on the needs of your platform and what seems to be working better, you can end up mixing things with a simple, just linear combination of them. And then in that branching model based, right? What it does is uncover latent factors representing user preferences and item characteristics. So instead of actually holding a vector for, actually, let's just get to the math. So CF will start with constructing a user item interaction matrix. We call it R with users, items, and the relevant utility to each user from each item, representing known interactions between users and items, right? So we have matrices here, one for the users, transpose, multiply, mapmul by the items, get out the actual rewards the users receive, where U is a K by M matrix, with K being the number of latent factors and M being the number of users. This is interesting. So model-based CF, right, its whole purpose is to uncover latent factors, not the actual, rather than working on a per item per user level, it works more on a trying to uncover the underlying actual important variables that determine what a user likes and what an item is and what an item makes an item useful, where K is that number of latent factors. And this is, keep in mind, this is like the model's embedding dimension for an LLM or something. This is a number you kind of just have to choose when building your model, and bigger obviously means more computationally intensive, but also more expressive. And then M being the number of users, and then I is a K by N matrix where N is the number of items, right? So the actual dimension being multiplied along ends up being this K right here, and R ends up being an M by N matrix, giving you the utility that each user would find from each item. Now, of course, you do a full model, it's not going to actually be just simple two matrices unless you're being very, very simple with this. A more deep learning version would still have these as inputs and that as an output, but a more complicated layer of hidden neurons or a full transformer or whatever in between. The two big challenges with this one is computational complexity, as already stated, given that you now have to not only have the quadratic of number of users and the number of items, but you also now have to deal with this latent dimension on top of that. So it's like a k times the quadratic issue. And also limited interpretability. Now you don't have a per item measurements. Now you have these hidden variables that are just unclear as to what they are. The model doesn't bother to tell you what they are. And of course, as I mentioned earlier, we also have hybrid systems that are pretty simple, just a linear combination weighted sum. So you take one type of recommender system, multiply by some constant factor, and then another type, multiply some constant factor, add them together, and that is your final prediction as to how much utility a given user will have for a given item. The difficulty in hybrid approaches obviously being the actual tuning, choosing your alpha and beta. A lot of the time, alpha equal to 1 minus beta and etc. for more and more of these, but you don't actually have to be that way. That's more just to make it pretty. But you have to balance how strong each one is and figure out the best performance for a given level of balance between the two. Now we'll get into the actual models being used here. So the methods I said earlier, these are broad frameworks, this and this, where the focus is more so on the input and output, but the actual thing happening in the middle can be swapped out for any number of given deep learning models. Of course, traditional multi-layer perceptrons, probably the easiest ones. The benefit being you no longer have linear interactions, you get some non-linearity in there. However, it is just a very simple add-on of complexity to not that much benefit. Non-linearity is huge, don't get me wrong, but still does not quite have the same level of benefit as something like a ResNet. The risk of overfitting is huge with MLPs, especially with small data sets, if you're like doing multiple epochs over them. The lack of spatial invariance, MLPs have no sense of which user is which or any of these issues. The equivalent thing in transformers and LLMs would be a lack of positional encoding. Vanishing and exploding gradients and explainability, of course, always issues with something like that. Autoencoders, right? These themselves have basically the same issues, but also their own levels of finickiness. Now that you have to mess with the noise in them. We're not going to, as I said, we're not going to be going in depth or anything into these actual deep learning based inputs into an actual full recommender system. I'm just running through some of the difficulties with them if you choose to go by them. Pros and cons, I guess. Convolutions, right? They have trouble with very sparse data or being scalable and just domain specific wise. A big part of RS, of recommender systems, the issues is domain specific issues, is a given different type of place where you might want a recommender algorithm, then a given architecture might not work with that domain based off the actual structure of the data, whether it's e-commerce versus social media versus whatever it might be. RNNs have, of course, the challenge they always have with exploding and vanishing gradients. More importantly, training being sequential. In order for to use an RNN, you have to, for some reason, have sequential data in your recommender system for some reason. Now, the big boy here, my impression of what is most common, this is in the advanced section, are graph-based systems for graph neural networks. We're not going to get deep into how graph neural nets work or anything. I am by no means an expert at all. But for a graph, it's defined as or denoted as G. It takes as inputs V, which are nodes being users and items. And here's the more complicated part as opposed to earlier, an E representing user item interactions. So it's nodes and edges, hence a graph. And in this case, the edges are actually important and mean something, whereas earlier, back in these first two math scenarios we showed, they're almost equivalent to only having one type of edge, so a much less expressive form of a graph. Edge being a connection between two nodes, between a user and an item. And the benefit GNNs have over that is the fact that they can have multiple edges for one thing. And so while nodes are users and items, in reality those users and items are represented by a feature vector. And the core operation of GNNs being that every given node reads off information from neighboring nodes and uses that to refine its features. With this process is what represents the actual user item interactions. Again, with the same prediction function as earlier, with the same goal to estimate the interaction likelihood between a user U and an item I. So just if the user is shown this item, what are the odds that they'll actually click on it? Now, sequential recommendation is more important in times where your actual data has a fundamental time characteristic to it. RNNs are probably useful here, and it considers the interaction histories of the users to predict future behaviors of users or preferences. So instead of representing the actual user as just characteristics describing that user. It represents the user in terms of the history of said user and their interactions in the history. In contrast, session-based RS focuses on short-term user activity for real-time recommendations. It doesn't care about the entire history. It looks at the current session of what the user is doing right now is a good metaphor for why they're using that word. And so sequential RS models can be thought of kind of autoregressively, where you put in the history, run it through the actual function, and you get out the next prediction, the next recommended item. And then you might, for example, pair that with the user's interaction, whether they chose to interact or not, and then add that back onto the history added on there and throw that back in again as input to again get the one after that. Whereas a session-based RS model is just looking at your current behavior, running that through the model and getting out what it believes should happen next. Now we're getting into language models and how they can enhance these systems in some scenarios. BERT is a good example. We used BERT embeddings for it seems like everything a few years ago. This was big for giving characteristics to an item from dialogues about that item, probably more like the reviews on a website, for example. If someone leaves a review, it's probably much more data rich to turn that review, that dialogue, into BERT embeddings and use that than it would be to just take that single data point of that user left a 5-star rating. An interesting one I was made aware of recently is a prompt in context learning based approaches where basically LLMs, as we know, just seem to be so good at doing a bunch of random stuff that what you can actually do is personalize a prompt and then provide information on the user and maybe even the items and use the LLM to then provide recommendations based off of that. I had a friend recently who he says all he uses ChatGPT for is he will tell it songs he likes or movies or TV shows or books he likes, and then ask recommendations based off of those. And because it's just has such a in-depth understanding or memorization or whatever of so much of culture in the world, he said it's pretty good at filling in the gaps for him as parts of culture that he missed on some genre of songs or whatever it is. And I'm sure with some more advanced techniques and providing maybe BERT embeddings or something, or just item reviews as inputs, that you could get some recommendations out of this. This again, though, is more so in a pinch. Obviously, LLMs are very computationally intensive. TikTok is not using those at all for what it's doing. This is more so for personal recommendations if you want those, or if you have a relatively small use case where you know you're just not going to collect enough data to make a standalone model. LLMs are a pretty good stand in, assuming you also have some kind of natural language basis with which to describe your users and your items. Big negative of them being not just computationally intensive, but also and RAM wise and everything, but also popularity biases. They just want you to watch or listen to whatever is most popular. But in terms of the cold start problem, they're super useful for that. Now, a big trend in this field are specialized systems, meaning systems that are really just designed and tailored to meet the needs of a specific domain, business, industry, whatever it is, that might have specific types of data modalities or whatever it may be. So, prior stuff we discussed may count as this. Context aware recommender systems are advanced systems that enhance the personalization of content by incorporating contextual information into the process. Unlike traditional systems that usually just rely on users and items interactions, CARs, these context aware systems, consider additional information like time, location, social setting, user behavior patterns, weather, I don't know, but they bring in outside data that is not just direct data on the user and the item. Already described this earlier. Review-based RS is just when they actually use written reviews by humans to generate personalized recommendations. A lot of times with LLMs or with BERT embeddings, but can be with other models as well. Aspect-based recommender systems extract and analyze specific product attributes from reviews, providing tailored recommendations to the user based on item aspects. So it actually purposefully creates categories of qualities of said items. This is slightly different from review-based RS. Review-based apparently just assesses the overall user sentiment and preferences, whereas aspect-based makes an effort to pull out specific qualities as that it can actually strictly categorize the item into. This often involves the introduction of lightweight ontologies to make it actually work, meaning you might design a set of relevant facts about the domain of interest, keywords, categories to put things into, stuff like that. A big difficulty with these systems is fairness, not just for like wokeness fairness, but also for business reasons of you want to provide the best recommendations possible to get the best results possible. And sometimes you have populations that are just not well represented, don't have a large enough sample size. And what you have to do, there's a variety of techniques, most often resampling, meaning you're disproportionately trying to sample those rare groups. Now, getting on to near the end here, broad limitations. The big thing here is just domain specific challenges. Is your business an e-commerce or a social media, yada, 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 yada? Um, your domain probably has unique data modalities and granularities and types and whatnots, and that can seriously affect which methods are available to you, which methods are computationally feasible for you. You know, TikTok cannot use a very computationally intensive method like a full-on running an LLM to do everything because it just needs too much. It wouldn't be feasible. And also ethical considerations, but it needs to be flexible and scalable enough to actually be deployed is a huge issue. Whereas a lot of AI models are still very much in the research phase or even just in the being subsidized by big tech phase and not making any actual money like LLMs right now. RS systems actually have serious business use cases immediately and profitably, and so they need to seriously work within a given organization's budget constraints, compute capacity, etc., etc. When you look at the basic inputs in the field, or I mean basic starting blocks in the field, matrix factorization based models, aka what I first described. Uh, they're considered the standard for like RS theory and learning, but obviously not actually that useful in real world scenarios. The being linear just kind of sucks. Inadequate latent feature representations and just the linearity especially. They're good starter intro models, but they're not actually useful for any real world scenarios, is what it sounds like. And deep learning solves that obviously, but as the volume of data grows, and a lot of the time, recommendation systems can have a lot more data even than what you might see with LLMs or something. These deep learning methods just hit computational limits. Another huge problem is data sparsity. A lot of these systems depend on strict user feedback. Something like TikTok, they're pretty good about using the dense data of just do you swipe or not? How long do you last on the actual TikTok? What are your eyes looking at? Like they track the hell out of you, right? But a lot of systems, like for example Netflix, the data that they actually can use reliably that actually works, such as leaving ratings, is very sparse. Very few users actually leave ratings or likes or whatever it is, and those who do only leave it on a very small percentage of the actual movies or whatever it is that they watch. So sparsity being a huge problem. How do you recommend uh, to users based on sparse data? The big issue in the field is the actual metric with which to validate them. Traditionally, they use accuracy with predicting the chance that a person will say yes, will download or hit the button on some item on an e-commerce site or whatever it is. But accuracy is not quite ideal, doesn't really encapsulate the full user interaction, mainly in the sense that users not only want accurate recommendations, like precision, but they also need versatility and diversity. If you show them the same thing over and over again, even if you were correct at first, they're going to get bored. And so that ability to actually have not just depth, but also breadth is huge. Another huge issue is just the inherent nature of this being a very correlative discipline. What they want in this field is they want causation, but all they really have to go on most of the time is correlations. So it's probably pretty frequent in this field to find you have a model that seems to perform well, at least in testing, but then you get to actual deployments and it kind of falls apart. So an active area of research here is a lot more like A/B testing that you would see in psychology or medicine or traditional science, and trying to identify the actual causal factors. What variable can we manipulate to actually get out causal information as to what's happening? And at that point, you're leaving AI machine learning entirely, and you're getting into just more traditional science. Another emerging line of research is trying to do all this computation on device with some very, very tiny model that doesn't need all that storage or computation resources. The difficulty being, how do you actually take in this information from others, from peers, and use it collaboratively and not have to download every single other TikTok video on the internet and figure out which are best? On top of that, the fact that each user's device is actually different, making this a big challenge. All right, this intro is very casual, obviously, very, very high level. I wanted to touch this because it's just good to see what other subfields are doing, even if they're not super up my alley per se. Hope you enjoyed. Like, subscribe, comment, all the YouTube things. Join the Discord to discuss. Follow on Twitter and LinkedIn. And support me on that YouTube join button down below if you're so inclined, as low as $1 per month, maybe more, and you will get early access to videos before they come out. You can also support through Patreon or Substack. Only YouTube gets the early videos, but all of them get the unique Discord role. And yeah, end of video.